Hello and welcome to Mac Sourcing. This is Bhaumik Dave, and you are watching my video wherein I'm going to show you how you can conduct static structural analysis using Salome Meca. Salome Meca is an open source software, so it allows you to conduct all the kind of FEA analysis, which is very popular in industry, such as static, structural, linear, nonlinear, isotropic materials, as well as non-linear material. Again, I think I repeated it: vibration analysis, modal analysis, then thermal analysis. So many kind of simulations you can perform, which is good because the software is free. And in my previous video I have showed you how you can calculate the matrices using a spreadsheet. Before we get started in any software, say for that matter, say in today Salome Meca, you should understand what are the inputs required for any FEA calculations. And I highly recommend you that you go through that video first and note down what are the parameters we calculated there. And so now I'll switch my screen and open Salome Meca. I hope that you guys are having it downloaded in your system. If you haven't downloaded yet, I recommend you that you download from the link on the top, which is Codeaster Windows, and you should download the 2019 fix version. So once you do that, now I'm going to switch my screen. So I believe my screen has been switched, and yeah, here it is. So I'm going to open first I'm going to open Salome Meca. So in my system, it is this folder SM 2019 W6412. So run underscore Salome is the command. I am just double clicking it. And I believe that you are also doing it in parallel by watching this video. So once you open that, you will see a nice looking GUI like this. And now here at the drop down menu, you can see a lot of modules. For us in today's video, the most important modules will be Aster Study, Geometry, and Mesh. But before we use this software, let's see what is the problem we are going to solve today using this. So this is the problem. Like, it is a 50 by 50 and 200 length bar having a load, an equally distributed load equivalent to some force here. So this face will be subjected to force, and this face will be fixed. Now we need to remember, like the left face or right face, whatever face it is, we need to fix one of the faces and apply load to another face. Why I'm telling you this is because when we use this module, we will first use geometry. So geometry has opened up here, and you can see a nice looking workspace here having a lot of option at the top. There is a new entity, then operation, repair. So basically in this environment, you can create the geometry, and you can also import any step file or any of STL file or any IGES file as well. So for today, for that matter of simplicity, we are going to only create the geometry. Here we have an option called new entity, and then primitives, and I'm going to use box. So our box size is 50, 50, 200. So I'm going to take the long dimension in X direction, and other two in Y and Z. So geometry is done. Simple. Now, do you remember I told you that one face we need to fix and one face we need to apply a load. So we need to tell the software, or rather we need to copy that surface into a variable. So for that matter, there is an option here It's called groups, defining groups, group, create group. Now, once you do open this tool, you will see a lot of options here like point, edge, and then this one is for face, and this one is for body. We are going to use for this the face, because we are interested into storing the faces. So first you need to select the master geometry, which is the box, and here we can write down the name. I'm just applying fix here. So once you select the main shape, now it should allow, and then what type of shape we want to select, entity we want to select, then it will allow you selection. You can see the color changed of the edges here as I move my cursor. So now I'm going to select this face, add. I'm going to click apply, because I also want to store another surface. So apply, and then another surface, change name, force, add. So now this surface has been added to a variable, a name called force. Now I'm going to apply and close. You will notice that whatever command you apply after that, see, this one only one face is showing up, the other two will be automatically hidden. You have to manually click this I button so that they are visible. Let's save this project for once. Try one, or let's say static. So I believe that the geometry part is over, because we are not going to define custom meshing sizes. We are going to choose the whatever mesh the software creates for. So uh, then we will move to meshing. Now remember that geometry groups we have created are only for that module. They don't belong to the meshing yet, because we haven't created mesh yet. So in mesh, just go to mesh, create mesh. The geometry will be automatically selected, and then you can assign a hypothesis, whether you want a hexahedron, whether you want a tetrahedron. Let's say hexahedron. I'm just selecting the default size, and then compute. Now the geometry groups are here only. Here we don't have that, so we can convert or bring them here. There is an option called create groups from geometry. So let's say this is element, and same way I'm also going to make a group for nodes. Now similar thing for force, apply and close. You can see the group of face for the entities like this. You can see the nodes like this. So meshing is done. Now I'm going to transfer this into Aster study. Aster study, we are going to apply or assign a finite element, because the meshing module, what it does is it just divides the geometry. It will not assign any physics to it. So if you remember, wherein we assigned an element like this, so it is what we are trying to do here is we are trying to the software that assign a particular element. But before that, we need to add a stage. So added a stage. Then first is read a mesh. By default, whatever mesh is available for this project, it will show up here. Mesh file format is MED. Okay. If you have multiple meshes, then you have to use it differently. You have to import all one by one. There is also another interesting way wherein you can apply commands and import many meshes at once. So that is a quicker one. But it is after you reach to a certain level of expertise or get acquainted with the software. Then for now we'll use the manual import, and now we are going to define the elements. So go to right click it, so it will, the options will come here. Then go to model definition, assign finite element. So click here. For now I am clicking everywhere, and then select mechanic. You have to also select this modelization, which element. I'm selecting 3D. So 3D element is applied to the model. Now we need to define the material. Make sure that your unit system remains consistent, because in geometry we created a 50 by 50 by 200. The software does not recognize whether it's mm or inches. So you have to be it is your responsibility. You have to be consistent with your unit system. If you are using make sure you use the similar units, or for all the other parameters you use same units. So I am selecting linear isotropic element. A linear is with an elastic limit. Isotropic is all the directions, the material properties are same. Young's modulus for now 200,000 megapascal. Poisson's ratio of 0.3. I'm not applying density. Okay, I think some, yeah. Okay, I double clicked it. So 200,000, 0.3. So now it has come. So this is we have just applied the defined material. We have not applied it to the model. Now we are going to apply it. Assign a material. We are assigning to mesh, and then which one? So if you have multiple materials, we will apply using a different thing called group of element. But for that, there is a different procedure, because you have to create all the group names. So here by default the material will come. Okay, I would have created this. Rather, I prefer this option, applying to the model. So for rotation, you can use the left mouse click button, and in geometry you have to use control and right mouse click button for rotation, for rotating the geometry there. So now the material has been defined. Now it is the time to define the loads. So there is a option called boundary conditions and load. Assign a mechanical load. Remember that one phase we are fixing and one phase we are applying a force load. First, let's start with the fix phase. So group of node, go to edit, and whichever group you made in the meshing module, it will come here. So fx is fixed, so you can visualize here. Okay, and dx dy dz, that is we are fixing this, so making it 0. Okay, now it's a time to apply the phase load, force on the phase, again to the same command. But there is an option, force phase, yeah, this one. Go here and then fz, because I want to apply it in this direction. Let's say minus 200. Okay, because I haven't selected the group of element. Now the force. Okay, remember that for this example I have not converted any units or anything for even for Young's modulus. I have just inputted it in megapascal, whatever value I remembered I input. But while conducting the real time analysis for the actual part, we must make sure that the unit systems are consistent. So okay. So load 0. There are two loads are available. One is fixed and another one is force load. Now the software still does not know what kind of analysis you are trying to create. You have to tell it using the analysis. Whether it is a static, it is a dynamic, you are trying to solve a thermal, what kind of scenario you are trying to solve. So let's say we need to use it in this case static mechanical. Now what is the material? This one, structural element characteristic is something different, which I'll show you in some of the future videos, what the option is for. Model, you will see here. Loads we need to select. There are two loads, so I am clicking it for twice, and this is the first load. Okay, and here I have to select the other load. So there are two loads here. The file name is Resilin, that is by default. So now the analysis is done. Analysis has been selected, not done, but we need to now define the post processing. Post processing, all these things which we were doing up till now, it is called pre processing, because before analysis is a process. Before analysis, whatever happens, it is called pre processing, and after the analysis, whatever we solve, whatever the plots we do, whatever results we study, it's called post processing. So here we need to define what post processing calculation, what stresses calculation it should do in addition to the default. The normal scenario, we study the von Mises stress, so I'll be defining that criteria here. Post processing, first one, cal underscore champ, let's say Resilin. Yeah, we need to select that. So sigma alga is the stresses calculated at the integration points. Sigma alno is the stresses calculated at the nodal points. So for now, I'm going to select both alno and alga. Criteria is wherein you can define whether it's a von Mises or other criteria. So SI EQ is equivalent stresses. Second one, alga. Result, Reslin. Okay. Most of the things are done, except we are not telling the software where to solve where to store the output file. So that we will do it using defining output and set output results. We have to define here resilient.midi. I have already a file name like that, and then what result it should store. So we will say that the result which is calculated here we should store. Format mid. So now the case is set up. So if you look at the left side of this menu, there are options: results, case view, history view. We will go to history view. So this case, current case, by default it should come here. You should click here first because it will keep the results. Otherwise, the next case when you run, the result will be gone. Click. Okay. it needs us to save it first. So saved it, then run. Now it will take some time depending upon your system. My system, it has already solved. So there are files available here. Reslin.med, if you remember, that is the file we defined to store our result. Just right click it and post process. So you will see some plots here, and with some displacement values. You can also see equivalent stresses at nodes, at integration points. Here there is a component. One might say stress car, what kind of component you want to select. So this was it for giving you an overview about how to conduct the analysis and what is the process we need to follow. And I believe that it helped you to just learn the methodology and overview to go through the analysis part in Salome Meca. So you can start your first simulation and keep looking at my future videos for more tutorials like this. Thank you. And if you like this analysis, if you like the way I showed you how to conduct the analysis in Salome Meca, you share it within your network. You can also subscribe to my channel and like it if you really enjoyed the video. Thank you, and I wish you a good day ahead. Bye bye.